Hey guys, welcome to the next module of this Learner Space course on device physics. In today's module, I want to talk about statistical mechanics and how we apply this to semiconductor materials. And I just want to give a warning that the math involved here is going to be a bit hand wavy, and the purpose of this module is to give intuition as to what formulas we're going to be using in the future lectures. Cool. So why at this stage why do we care about statistical mechanics, right? We know that the behavior of each electron is governed by Schrodinger's equation for the system. So the issue is that you cannot literally go and try to solve Schrodinger's equation for each individual electron to understand how the system as a whole works. Just like how in thermodynamics, which you may have studied earlier, you cannot, in principle, you can solve Newton's law for each atom in a thermodynamic system, but in practice that is not possible, right? That is why we introduce like some statistical thermodynamics. So this is very analogous to that, and that is why we invoke some statistical methods. And what we are also able to do when we invoke these methods is we are able to actually make like this, like the approach, we can change it from quantum, purely quantum mechanical, to something which we call semi-classical, where we can still apply some of our intuitions from classical mechanics. Cool. So firstly, we're going to talk about what is the probability that an electron takes some energy level E lambda. So I just want to be very clear about what I mean when I say this. I don't want it to go ahead and become confusing later on. This is not the probability that the state E lambda is taken, but it is the probability that if I give you an electron and I ask you that, okay, there are states E1, E2, E3, E4, E5, what is the probability that this particular electron is in E1? That is what we mean by that. So electrons can take any energy levels. What is the probability that a given electron takes the energy level E lambda? And this probability is given by this factor which is shown here. We are not talking about the scaling factor, but we are just saying that it's proportional to e power minus e lambda by kt. So this is the claim we are making, and it's something that can be derived by statistical mechanics, and it is beyond our scope in this course to derive. But I just want to give you a flavor for why this is intuitive. Firstly, like E lambda itself, the higher the energy level you go, the lesser the chance that the electron occupies that particular energy level. Again, I want to be clear, this is the probability that a given electron occupies some energy level. It's not the probability that the energy level itself is occupied. Cool. So the higher the energy, the less likelihood that the electron occupies that. And that is captured over here. When in the negative sign, if you like increase the value in the negative sign, then you get closer and closer to zero, which means your probability reduces. Whereas in if you increase the temperature, we know that when you increase the temperature, then for a given energy, the likelihood increases. Like supposing my E lambda is the third excited state, for example, then the likelihood that my electron takes that third excited state increases with temperature. That means that like for a given higher energy, if I increase the temperature, the probability should increase, which again corroborates with this exponential term. So that's why it's a reasonable result. But the exact derivation of this is something that is beyond the scope of what we are currently dealing with. Cool. So now we want to eventually move on from what is the probability that a given energy level is occupied, that a given electron occupies some energy level, to the probability that that state is actually occupied. So, what 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 we're actually now moving to is the occupation probability of some particular state. So let's take the state E lambda and let's talk about what's the probability that this is occupied. Now, the way we do this is we calculate the average number of electrons in E lambda, and since there can only be 0 or 1, the average is the occupation probability. So if I tell you that in the cases where I flip a coin and I get a head, I assign the value 1, and in the cases that I flip a coin and I get a tail, I assign a value 0. And then I tell you that the average after doing this for many turns, say it's a biased coin, and the average I reach at is 0.6, then you can tell me that the probability of our heads is 60%. So similarly, since that E lambda can, the average number of electrons in E lambda can either be 0 or be 1, the average becomes the occupational probability of the electron, just like the average became the probability of heads in that case. And we can easily write this probability in terms of this formula that we've given on the screen, which is that n lambda is summation n lambda times the probability to take that state upon the summation of the probability to take that state. This is like probably a formula for average that you have even probably learned in like plus two. So it's the same formula. The reason we have n lambda inside the exponent is that the probability that n electrons happen to be in a certain state, if we consider them to be independent events, is uh, is the product of the probabilities, and when you have that product in the exponent, it gets added up. That's why you have n lambda here. And note that beta here is just 1 by kbt that we had in the last slide. So this is the formula for the average using basic definition of average and what we had on the last slide, which was the probability that given electron takes some energy state E lambda. And basically we now allow the values of n lambda to be 0 and 1, because either the energy state is not occupied or it is occupied. You cannot have two electrons in some particular state, right? So we sum over 0 and 1, and when we do that, this is what we get as the result for occupation probability. So using the result from statistical mechanics, which was that what is the probability that a given electron occupies some state E lambda, we derive the occupation probability itself of the state E lambda, which means that this is the probability with which E lambda is occupied by an electron. So yeah, that is the that is what we have achieved in this derivation. Cool. So now that we've talked about what occupation probability is and what the expression for that is, why do we care about occupation probability in the first place, right? So the reason we care about this is that if we can add up all the states in a band times the occupation probability of each of them, then we can get the average number of electrons in a given band. So say I know that there are like 10 states and each of them is occupied with some probability zero point 0.6, then I know that on average 6 number of states are occupied, and if each state then has 2 electrons in it, then I have to average of 12 electrons. Obviously this average becomes more and more accurate when you have a lot of states, but I just want to show you that in principle, once you know the occupation probability, you can like calculate these things. And this becomes incredibly useful since using this we can know the number of free carriers. So if I know the number of electrons in the conduction band and the number of electrons in the valence band, I can correspondingly calculate the number of holes in the valence band, and therefore I can know what is the total number of free carriers, for example. So this is why we care about this occupation probability. Cool. So now I want to talk about a new concept called the Fermi level. If you look at this original expression of the occupation probability, which we derived just now, you can see that with respect to the energy, this given expression is centered at the origin, which means that this exponential changes from positive to negative at the origin. And the origin also corresponds for all positive t as the energy for which occupation probability is half. What do I mean by this? What I mean by this is that for all positive values of t that are not zero, absolute zero, uh, if your energy is zero, that means your distribution is at the origin. That is the point at which your 1 by 1 plus e raised to 0 becomes half. So your occupation probability becomes half. So the what I'm trying to get at is that this expression with respect to energy is centered at the origin. And in general, absent any other information, there is no reason to believe that this distribution should be centered at the specifically at the origin. So this expression can be generalized by a shift in origin, and the fact like the constant by which we shift the origin is called the Fermi level, and we represent it by EF. So in some sense we refine this expression into a more general one by a shift of origin in the energy, like in energy. So again, like I had warned you before, this is a fairly hand wavy way of looking at things, but it's like just meant to give you some intuition as to how the expressions that we are going to use in the future. So yeah, what I want you to understand from this is that now you have shifted the origin to the point at which where you get the occupation probability as half. Now that happens at the energy equal to EF. Of course, provided that the temperature is positive. Cool. So moving on, let's talk about this Fermi level more. Like I said in the last slide, Fermi level is the energy at which occupation probability is 50% or one half for all t greater than 0, which you can clearly see in this expression for uh, Fermi level. Now at absolute 0, things are slightly different because at absolute 0, let's just look at this expression and then justify it, right? Fermi level is the highest occupied energy level. Every energy level below it is occupied and every energy level above it is empty. Now let's look at this expression for occupation probability at absolute 0, right? So now if your denominator goes to 0, right? And since temperature cannot be negative, let your denominator be 0 plus, right? Now for E that is less than EF, you have this exponential of the form of e power minus infinity, because your denominator is going to 0 plus and your numerator is negative. So if this is e power minus infinity, then this whole expression tends to 1, which is the first part of this expression, which is that every energy level below the Fermi level is occupied. And uh, of course, if you have E greater than EF, then your this whole term tends to e power infinity, and 1 upon 1 plus e power infinity tends to 0. So every energy level above the Fermi level is empty. So at absolute 0, this Fermi level gives us a Fermi energy gives us a different interpretation, which is that it is the highest occupied energy level. Every energy level below it is occupied and every energy level above it is empty. And like, I want you to pause and think about this for a second, right? Because if you remember in one of the previous modules, I told you that we fill energy levels from lowest energy to higher energy because that's the most stable way. And this is exactly what's happened here. The only difference is that because temperature is absolute zero, there is no chance that an electron gets to get some energy and jump to a higher level, which is why all the energy levels below some cutoff are occupied and then above that are empty. So yeah, just trying to give some intuition for the Fermi level here based on the things we already have intuition for. Cool. I want to show you this graph in terms of how your occupation probability looks as a function of E minus EF. So you have E minus EF in electron volts on the x-axis, and this is your occupation probability. And as you can see, at E equal to EF, you are always cutting the occupation probability of half for all these values of temperature. And if you can guess how this distribution would look for T equal to 0, if your guess is that it will look like some type of staircase, then you're right. Which means that for every E less than EF, your occupation probability is 1. For every E greater than EF, your occupation probability is 0. So this is how for the various temperatures, you can see how this occupation probability varies with E minus EF. The closer you are to 0, the more it looks like a staircase, right? And this makes intuitive sense. Cool. I just want to flag out that Fermi level is a quite an important concept, and that's why I'm spending a bit of time on giving you some intuition on it. Uh, so basically, because we see that Fermi level tells us that which is the state which is which is occupied with probability half, it can give us important intuitive information about which states are likely to be occupied. Because now I know that which is the energy level at which occupation probability is half. And because it gives this intuitive information, we generally show it in our band diagrams because our band diagrams are supposed to give us visual information. Now, if you like go through the last module, I had told you again band diagrams. I'm just reiterating. It's energy level versus your coordinate, right? Cool. Now I want to talk about some intuitive observations about the Fermi level. Firstly, energy levels below the Fermi level are more likely than not occupied. By more likely than not, I mean with probability greater than 50%. So this is something which we saw again on the last, on the expression of the Fermi level itself. So if you're below the Fermi level, the likelihood that you're occupied is more than 50%. If you're above the Fermi level, you are more likely than not occupied, which means the probability that you're occupied is less than 50%. The further below the Fermi level you go, the more likely you are to be occupied. Again, you can go to the expression of occupation probability, and this will be very intuitive, right? The more negative you go in the exponent, the more that probability converges towards 1. And the further above the Fermi level you go, the less likely you are to be occupied. So again, Fermi level, you can even see the graphs on the last slide. Fermi level is 50% occupation probability. As you go more and more towards left, your probability tends to 100%. As you go more and more towards the right, your probability tends to 0%. Uh, Now, one last intuitive point that I want to give you. If the Fermi level rises as your x coordinate increases, for example, if you're moving in x and you made a band diagram and your Fermi level rises as x increases, crudely what that means is that the average electron on the right has higher energy than the average electron on the left, and that tends to mean that your left side is more stable than your right side, and you can probably have some electrons jumping from the right to the left. So again, this is the examples of stuff I'm trying to show you, that how we can intuitively use these things. So uh, you can clearly see that the average electron where the Fermi level is higher will have more energy than the average electron where the Fermi level is lower, because the Fermi level represents the point where probability of occupation is half. Cool. Just some recaps of the key learnings in this module. First is that statistical mechanics gives us macro level information. We spoke about why it matters. The occupation probability of a given state is given by this expression with respect to the Fermi level. We tried to see how intuitively this expression comes about. Note that EF here is one quantity, the Fermi level. I've forgotten to subscript the F. Finally, intuition about the Fermi level. It is kind of the origin of this probability distribution. It represents the energy level with occupation probability half for T greater than 0. For absolute zero, it represents the highest occupied energy level. All levels below it are occupied, all levels above it are not. And finally, it gives us intuitive information about which states are likely to be occupied and which are not, right? So these were the key learnings. In the next module, we are going to talk about density of states, and that's similar to what I explained on the slide of why we care about occupation probability, and how we are actually aiming to get information about the number of free carriers from that, right? So hope you guys enjoyed this one. See you in the next module.